Okay, thank you very much, and thank you to all of the organizers for inviting me to give a talk here. I've left quite a bit of time for questions, so do feel free to ask questions in between or in the end. So what I wanted to talk about today was some recent work on Gaussian process regression, and in particular some convergence properties of Gaussian process regression. So the outline of my talk is just the following. So I'm just going to start with the problem formulation. So just stating the problem that I'm going to be interested in solving, just so that everybody's on the same page. I assume not everybody's familiar with Gaussian process regression, so I'll go through the setup, how Gaussian process regression works, and kind of what the important things to think about are. And then I'll show you some theoretical results on convergence properties of Gaussian process regression, and then some conclusions in the end. Okay. So what is the problem that I'm interested in solving? So I'm interested in solving this problem here. So I have some unknown function f defined on some domain U, for simplicity scalar valued. Everything extends to vector valued as well. I'll stick to scalar valued for this talk. So I have some unknown function f. What I know about the function f is just this data y. So I have these n function evaluations. So I just have some points in the domain of f and the corresponding function values, and I have a finite number of those. Okay. So given these function evaluations, I then want to learn what my unknown function f is. For most of the time, I'll be talking about exact function evaluations. So you're really given f of u. You can also extend everything to the case of noisy function evaluations, where we have some noise, and if you're interested in that case, then please ask me in the end. Okay. So this is the problem that I'm interested in. It's a very general problem, so I'm sure many of you have seen this before. So it appears in very many different situations and application areas, right? So one example is, for example, in machine learning applications where you want to do prediction. So you have some training data in this form of input-output pairs, and then you want to do some prediction of what you think the output is going to be at a new input. But it's also a classical numerical analysis problem in terms of interpolation or regression, and also reduced order modeling quite often fits into this framework, where you have some very expensive function f, and you want to construct a surrogate model for f, and you do that by kind of choosing a small number of function evaluations and then constructing a reduced order model from there. Okay. So it's a very general problem and an important problem that appears in very many applications. And I probably also don't need to convince you that it's actually not an easy problem, right? So it might be very easy to state, but solving this in complete generality is really a very difficult problem if you don't really know what the function f is, and you don't really have any restrictions on what f is, right? So f could be a multi-scale function that has very different length scales involved, or it could have very steep gradients or things like that, which make this problem very difficult. So the way that we're going to solve this problem is in a Bayesian statistical framework. So the solution to this problem is for us going to be a probability distribution, particularly the posterior measure that you get on the function f conditioned on your observations y. Okay. So this comes from a Bayesian statistical framework. And so what that allows you to do is to also have uncertainty quantification in the recovery. So you get this whole probability distribution on the unknown function f given y. So you don't just get like a point estimate, which tells you what you think f is, but you also get some information about how certain you are in your reconstruction. The question that I'm going to be interested in for this talk is sometimes referred to as posterior consistency. So I'm interested in what happens as n tends to infinity. So as the number of data points that I have goes to infinity, intuitively you should be able to recover your function f more and more accurately, right? And you kind of hope that as n tends to infinity, you're able to recover the true underlying function f. Right? So phrasing that mathematically in this context, we then look at the posterior distribution that we have, and essentially you're interested in whether this posterior distribution tends to derive on the truth. So the mean of this posterior converges to the true function f, and the variance goes to 0, so that you're really kind of concentrating on the truth. Yeah. So that's what we're going to be interested in. Right. So Gaussian process regression is now just a particular example of this. So Gaussian process regression is a particular instance of this Bayesian framework. And in particular, it just corresponds to a particular prior distribution on your unknown function f. So Gaussian process regression, you do the standard Bayesian prior to posterior update. So you choose a prior distribution on f, you condition it on your observed data to then get the posterior. So the first thing that you have to do is choose your prior distribution. As I said, in this case, we choose it as a Gaussian process. Gaussian process, like a Gaussian random variable, is specified by its mean and covariance. In this case, we have a mean function, which for simplicity I've chosen 0. You can also do everything with non-zero mean. And then you have a covariance kernel, which I denote by k. If you're not that familiar with Gaussian processes, I've given you the definition here. So that we're modeling, or that we're saying that f is a Gaussian process, that means that at every point ui in the domain of f of ui is now a Gaussian random variable. And in particular, if you look at the joint distribution of f of ui at any finite collection of points, that's going to be a multivariate normal random variable. The mean function that you've specified gives you the mean, so it gives you the mean of f of ui at the point which here we've chosen to be 0. And then the covariance kernel is what gives you the covariance of f at different points, the covariance of f at ui and uj, that is given by your covariance kernel k at ui and uj. So you can think about it visually as well. So you've now chosen a probability distribution on functions. You've chosen a mean function, which in this case is just the 0 function that I've chosen here. So this black line. And then you have a kind of variance or pointwise variance as well. So at every point, you now have a normal random variable that has this mean, and then it has a given standard deviation. And so what happens is that realizations or sample paths of your Gaussian process then look something like this. So you get something that stays close to the mean, which is 0. And then you get something that fluctuates around the mean, and the fluctuations are kind of the size of the standard deviation that you've chosen. Right. So as I say, it's just one particular way of defining a prior distribution on your unknown function f. And then once you've done that, you then do the standard prior to posterior update. So you then get the Gaussian process posterior. So it's the posterior distribution now on f given y, where y were these function evaluations that we had. If you choose the prior to be a Gaussian process, the nice thing is that the posterior is also going to be a Gaussian process. So that's one of the reasons why Gaussian process regression is very much used in this context, that you can actually write down this posterior distribution on f given y explicitly. You know that it is, again, a Gaussian process, but with an updated mean and covariance function. So the mean and the covariance function will get updated dependent on the observations. Exactly what the mean and the variance are is not that important. For this talk, you can write it down explicitly, so it will depend on your observed data. So here you have the so the f of dn here, that is just the vector of function values that you have. So the f of un, just the vector of that. And then the other things that appear are just the covariance kernel k that you chose in your prior. So you can write it down explicitly. Again, visually, the mean and standard deviation get updated. So if we now have observed the function values that are in these points with the black dots, the mean then, for example, gets updated to this black line, right? So you're conditioning the process on going through the observations. So the mean always passes through those observations. You can also see that at these points, the variance becomes 0. Again, that's because you're conditioning the Gaussian process to go through those points. So in particular, every sample path that you see here will also go through those points. And so the variance at these points is 0. Whereas in between the sample points, the Gaussian process kind of is still varying and can still do different things. And so there is still some variance in between the data points. Right. So that is a quite simple version of Gaussian process regression. So you can do a bit more complicated things as well, but this is really the simple setup. And so, as I said, in this context, you can actually write down this posterior explicitly. So the f given y, you can write it down explicitly. And so you might be thinking you're kind of done, right? So there's not really anything else to do. But in as with everything that you do with Bayesian inference, there's always the choice of the prior, right? So you still do have to choose a prior. And yeah, as I said, as with all Bayesian inference tasks, that's kind of an important task and something that is not always easy to do. Right? So in this context, what you would want to do is kind of choose the prior kind of in a good way to match your unknown function f, right? So you want to kind of choose it to reflect the properties of f. What do I mean by that? So the kernel that you choose, so because we've restricted to mean 0 for simplicity, everything is kind of determined by the kernel. And so the way that you choose this kernel kind of determines all of the properties that you get of the Gaussian processes, so the properties of the prior, and hence also the properties of the posterior. So what kind of properties do I mean? So I mean things like smoothness. So by smoothness here, I mean differentiability. So if you look at sample paths of the posterior, how smooth are they? How many derivatives do they have? So I've given you some examples here. So in these 4 pictures that I have here, each of the 4 plots has 5 independent realizations of a different Gaussian process. So all of these Gaussian processes here have different covariance kernels K, and you can see that the sample paths do look very different for all of the different kernels, right? So in the first row, what I've done is I've chosen a covariance function that gives you sample paths that are not differentiable. So they are continuous, but they're not differentiable. For those of you who are familiar with the area, I've chosen the exponential covariance function. So that's the covariance function of the Einstein-Uhlenbeck process, which gives you sample paths which are Hölder continuous with exponent less than 1/2. Right? And you can see they're quite rough. For the bottom row, I've chosen what's called the Gaussian covariance function. So this is a covariance kernel that gives you infinitely smooth sample paths. So see infinity sample paths, and you can see they are a lot smoother. There's also a property here which I called contrast. So this is really the marginal variance. So yeah, it's the marginal variance. So it's how much variation you get and how big the amplitude of the variations is. So whether when you plot these sample paths, whether you go between -4 and 4 on the y-axis or -40 and 40, so kind of the vertical length scale. There's also kind of horizontal length scales or length scales of fluctuations. So this is the correlation length scale of the kernel. And again, here I've chosen 2 different length scales. So here there's parameter lambda, which represents the length scale. Here I've chosen a large length scale, and here I've chosen a small length scale. And so in these ones, you can see that you mostly get kind of long range fluctuations, whereas in the right column, you can see that you get fluctuations on much shorter time scales or shorter scales. Right? So you have all of these different properties. You can also determine periodicity. So whether you have a function that's periodic or not, you can also do that with the kernel. And stationarity, so whether your function looks the same everywhere in the domain or whether it looks different in different parts of the domain. So whether you, for example, have on the left-hand side a very smooth function that varies on long time scales, and then on the kind of right-hand side of the domain, you have something that's very oscillatory. That would be something that's non-stationary. I'm not going to be talking too much about those things today, and I'm going to be focusing on kind of these 3 properties that I've highlighted in blue. So as you can see, the way that you choose the kernel K really determines what your sample parts look like. Right? And the problem is that you typically don't know what the right choice of these hyperparameters is. Right? So typically there's some hyperparameters in the kernel that determine these things. So there's this parameter which is often called lambda, which gives you exactly this length scale parameter. There's another parameter that gives you the smoothness and so on. And these are things that you typically don't really know how to choose, right? All that you know about your function f is these function values that you have. You don't know what typical length scales the function f has. You might not know how smooth your function f is. And so choosing kind of the right prior becomes very difficult in this context, right? So you might have a function that really looks like this, but you're assuming in the prior that it looks something like that. And then it's not intuitively immediately clear whether this is still a sensible thing to do, and whether everything kind of still converges to the correct underlying function. Right. So I'm going to show you some theory that actually shows you that this is the case. So the kind of main takeaway message from the talk is that this methodology is actually kind of surprisingly robust to these misspecifications. So even if you do have a function that really looks like this, and you're assuming your prior looks something like that, in most cases, it still works, right? So in most cases, you still kind of converge to the correct thing. So that was the main message, right? So how are we going to do this? So how are we going to deal with the fact that we don't know what the correct choice of these hyperparameters is? So you could do a fully Bayesian approach, right? So you can, as I said, do a fully Bayesian approach. This is a hierarchical Bayesian approach where you then obtain the posterior that you're after, so the posterior on your unknown function f given y, by first finding the joint posterior. So you then find the joint posterior on your unknown function f and the unknown hyperparameters theta conditioned on the data, and then you just marginalize out theta. Right, so that is something that's usually intractable. So integrating out theta in most applications, it's not possible to do analytically, and it's computationally too expensive to do computationally. So often that is not really an option. And so what you do is quite often this empirical based approach is often called also the plug-in approach. So what do you do here? So in that case, you compute an estimate of your hyperparameters. So you have this estimate theta hat that you're computing from your observed data y. So that's where the dependency on n comes from, that you're estimating it from your data. And then you kind of pretend that that is the true value or the correct value for the hyperparameters. And then you just plug that into your covariance kernel, into your prior, and then you just do the standard prior to posterior update. Right? So it's plug in the sense that you just compute an estimate for the hyperparameters, then pretend that that is the correct value for the hyperparameters, and then do the standard prior to posterior update. So how you actually estimate these hyperparameters is another question. So I'm not going to talk anything about that. Right. So there's still a lot of research going into that, how you can do that efficiently. And it's really kind of a whole topic on its own, how you can do that efficiently. You can think of doing things like maximum likelihood or maximum a posteriori estimation or cross-validation or something like that. What I'm going to be interested in is what happens as n tends to infinity and whether we can get this posterior consistency. So whether the posterior that we get on f given y, whether that still concentrates on the truth as n tends to infinity, even if we do have to estimate the hyperparameters. So this is, of course, a question that a lot of people have looked at. So there's a large body of literature on this question of posterior consistency. In particular from the spatial statistics literature. So I've given you some of the main references here. And what kind of results you get and what kind of proof techniques you're going to use really depends on what kind of setting you're interested in and what kind of setting you're working in. So the standard references that I've given you here, in the particular case that we're working in, don't really apply. So there's a couple of differences which makes those results difficult to apply. So for example, we're interested in the case where f is kind of a given deterministic function. So we have some true function f that we're interested in approximating. So for example, not assuming that f is a sample of the Gaussian process prior that we're putting on it, which is something that is quite often assumed in the other references. So a couple of other specific things. So we're interested in the design points being deterministic, the points un at which we're collecting function evaluations. These are assumed deterministic in our setting, and we have no noise in the training data. We're interested in the error, not just at the observation points, because we don't have any error at the observation points. So we do want an average error over the whole of the domain of f. And in particular, the fact that we're estimating the hyperparameters from the data. So these estimated hyperparameters actually change with n. That is actually something that is quite difficult to deal with in the analysis. So the analysis that we're going to use will come from the numerical analysis and approximation theory literature. So what we want to do is we want to have some form of convergence as the number of function evaluations that we have goes to infinity. And what we want to show is that the mean of the posterior, so the MNF, which was the mean of the posterior on f given y, that tends to the true function f, and the variance of the posterior, the kn, that goes to 0, so that the posterior kind of tends to a Dirac on the truth. Right. So there's two things that we can notice about the mean. So the mean of the posterior, as I said, we do have an explicit expression for it, and in particular, you can write it down in this way. So the mean is just turns out to be a linear combination of the kernels k for some known coefficients alpha. Okay. So what you have is just the function k here. Remember, and that was the covariance kernel that we chose in the prior. Okay. So the posterior mean is just a linear combination of prior covariance kernels. You also know that it is an interpolant, right? So the mean at the points where we have observed f, that is going to be an interpolant, right? Because we're conditioning the process on going through those points. And if we go back to these pictures, right, because we're conditioning, the mean does always go through the points, and you can see that it is just a particular interpolant going through the points. Right. So what this means really is that it's what's called a kernel interpolant, or that means that it is an interpolant and has these kernel functions as the basis functions, right? So the prior covariance kernel here takes the role of the basis functions in your interpolation. And in particular, if you have isotropic kernels, you get something that's very closely related to radial basis function interpolation, which is very well known in numerical analysis. Right. So because the prior covariance kernel k kind of takes the role of the basis functions, what kind of convergence properties you get, so what kind of convergence rates you get in n, and what kind of assumptions you need on your function f for this to converge, will depend on the specific choice of k. There's a really wide variety of results out there, so I just wanted to show you one or two particular ones now. So these results are going to be specific results for this family of Matern covariances. So this is something that's quite often used in applications. So this is a parametric family of covariances. So it has three hyperparameters. So our hyperparameters theta, that's now a vector in R3, which has these three entries, so the sigma squared, the lambda, and the nu. So the sigma squared is the contrast parameter, so that is the marginal variance, so the size of the fluctuations or the amplitude of the fluctuations that you have in the functions. There's the lambda, which is the correlation length scale, so the typical length scale of fluctuations. So if lambda is large, you get quite smooth functions that only vary on long length scales. And if the lambda is small, you get something that's very oscillatory and fluctuating on short length scales. And then there's the nu, which is related to the smoothness, so related to how many derivatives your function f has as a function of u. So the general formula looks quite horrible. You have the gamma function here, and then here this is the a Bessel function. It does simplify in special cases. So for special values of the parameter nu, it does simplify. So for example, when nu is equal to half, you get the exponential covariance function, the covariance function of the Einstein-Uhlenbeck process. And in the limit as nu tends to infinity, you recover the Gaussian covariance, or the squared exponential, or RBF covariance function, which is this one here. But in general, it does have a it does have these three parameters, which makes it really a very kind of flexible model, and you can kind of tune the different parameters to get different properties. So long length scales, short length scales, very smooth functions, or not very smooth functions. Yeah. So the result that you get is this. I'm going to spend quite some time on this slide, because there's a lot of information on it. So this is now a convergence result that tells you something about the convergence of the mean. So here we now have the mean of the GP posterior. This was the mean of f given y with the estimated hyperparameters, and you can show that that tends to your true function f. Right? So we here have then a bound on the L2 norm between the true function f and the GP posterior mean. The right-hand side will usually go to 0 as n tends to infinity, and so you get convergence of the mean to the truth. And likewise, you have a result on the posterior variance, so the variance of the GP posterior with the estimated hyperparameters, likewise will go to 0. So usually this thing on the right-hand side goes to 0 as n tends to infinity. Okay. The way that the number of data points n enters is through these two different quantities. So one, you have the
Rita, there's a question in the audience.
Yeah.
So, Rita, can you comment on this set U here? Mm-hmm. What is this set U?
Yeah, so U is the domain of f. U is the domain of f, and for this result to hold, we have to assume that it's Lipschitz and bounded, so bounded Lipschitz domain, and it also satisfies an interior cone condition.
Okay.
Yeah, so you essentially you can't have very sharp corners, so either going like inwards in the domain or outwards.
So it's very similar to the kind of things for the kind of estimate for finite elements in a way, or for other standard methods. Maybe you go in behind the proof, you go through other types of approximation in the background. I mean,
yeah. So it's essentially the assumptions that you also have in this book by Wendland. Yeah. So it's a very
Thank you. Thank you.
Yeah, yeah, no problem. Okay. Yeah, so the way that the dependency on n enters is through these two quantities. So there's the fill distance h, and then the mesh ratio rho. So the fill distance is a measure of how well your point set is kind of filling out the domain U, right? So what you do is you look at the furthest that any point U in the domain of F can be away from one of your interpolation points, right? So the dn were your function evaluations that you have, essentially your interpolation points. And then you're looking at how far away any point can be from an interpolation point, right? So essentially, if you want this fill distance to go to 0, you need what's called a space filling design. And so you need to really kind of fill the space with this design. And then in most cases, your fill distance will then decrease with n at a rate that depends on the dimension, right? So the du here is the dimension of the domain of f, right? So f is a function of du inputs. So that is the thing that then usually gives you convergence. So this is something that is decreasing in n, and then you get a certain rate. The rate that you get depends on the smoothness here. So you have the nu here, which is the smoothness of f. So I'm assuming that f is in this Sobolev space. So it's a standard Sobolev space of smoothness nu plus d over 2. And so you need d over 2, nu plus d over 2 square integrable derivatives. And then the other thing it depends on is your estimated smoothness. So yeah, your estimated smoothness parameter that you're estimating from the data. And then you kind of get the minimum of your estimated smoothness and the kind of true smoothness of your function f. The other term that comes in is this rho here, which is called the mesh ratio. So the mesh ratio is really a way of kind of measuring how uniform your points are. And it measures what in this community is called quasi-uniformity. So if you look at the mesh ratio, what it is you have the fill distance in the numerator, right? So here you're measuring kind of the maximum distance that a point u can be away from un, and in the denominator you have the minimum distance between two design points. And so what you're really comparing is kind of the maximum distance between two interpolation points and the minimum distance between two interpolation points. And ideally you would want that to be constant. Okay. That's the best that you can do. Okay. And so essentially what this means is that you can essentially get some stability issues if you have 2 points that are very close together, right? So if this minimum distance between points, if that decreases very quickly with n, then you can get some stability properties coming in. I'm happy to talk more about that if people are interested. Just a couple of more comments on the results. So the only assumption that you need on f is that it is in this Sobolev space. Right? We don't have any other assumptions on f, and then the assumptions on u that I just mentioned, that's a bounded Lipschitz domain with an interior cone condition. For the estimated hyperparameters, one, you don't need the estimates to converge, right? So the estimated variance, so the sigma squared and the lambda, they actually only enter the constants, so these constants c and c prime here. The estimated smoothness also affects the rates, right? Because that's what usually, that's what usually enters the rates in these kinds of estimates, how smooth you're assuming things are. For this particular result that I've written down here, you need these things to be uniformly bounded away from 0 and infinity. And there are some cases where, for example, it is known that maximum likelihood estimates either converge to 0 or infinity. The results can be adapted to that case. So you can track exactly how these constants c and c prime depend on the estimates. So you can deal with that as well. In some cases, you do get the optimal convergence rates. So the rates in n that you get from this are optimal in the sense that they are the optimal rates that you get for any function f which has this Sobolev smoothness. So if you have any function f with this Sobolev smoothness and you're using a method based on n function evaluations, these are the best rates that you can get. And in particular, you get them if you're able to estimate the you're estimating the smoothness correctly. In most cases, you can also get them if you're overestimating the smoothness. You can't get them if you're underestimating the smoothness. There is a penalty for overestimating the smoothness only if this mesh ratio grows with n. So if you don't have quasi-uniform points, if you have points which are very close together, then you can get some stability issues there, right? So essentially what this corresponds to, overestimating the smoothness, that corresponds to choosing a prior that is too smooth, right? Because if you think about it, the estimated smoothness nu hat n, that is then the smoothness that you plug into your prior, and the prior covariance kernel are the basis functions that you're then using. And so in that case, what you have is a prior that is, the prior is just too smooth in that case. Right? So if you're overestimating that too much, then you can run into some issues. Again, I know that was a lot to take in, so let me maybe just finish there, and if anybody has some more questions, I'd be happy to answer them. So I think I just have one more slide that I wanted to show you. So the rate that you get here, so as I said, in some cases these are optimal, so these are really the optimal ones that you can get for any function f in this Sobolev space. And in particular, you can see that they deteriorate quite badly with the dimension. So if f is a function of very many inputs, so if the input dimension of f is very high, then you get quite slow convergence rates with this method. There is a way of getting around it. So in that case, you really have to kind of develop a new theory. So these results that I showed you earlier, because they're based on the fill distance, and the best that you can do with the fill distance is this rate here. You can't really get any better convergence rates from this theorem. And so you really have to then kind of look at specific constructions and specific point sets and kind of get a new proof for those. So in particular, I wanted to show you this one result that is based on choosing the interpolation points, the design points where you evaluate your function f. You choose it as a small x sparse grid, right? So you can choose a particular built on just uniform points. You do have to choose a particular kernel. So in this case, if you choose your covariance kernel as the separable Matern kernel, so you are assuming that your kernel is just a product of the Matern kernel in one dimension. So in every dimension, you choose the Matern kernel with some parameters, and then you just choose the product of that as your covariance kernel in d dimensions. Then likewise assume that your domain of f is a tensor product domain, so you can write it in this form. Then you can get this result. So I haven't written down all of the details because the expressions are quite long, but you can find them in the paper. So in this case, what you can then show, if you use this particular construction, if your f has the right type of regularity. So we're now assuming that the f is in these so-called spaces of dominating mixed smoothness. So these are tensor products of one-dimensional Sobolev spaces. Your f has that regularity. You can then show that you get much better convergence rates. In particular, you get n to the minus alpha here, where the alpha will again depend on the smoothness parameter that you have. But in particular, it's going to be independent of the dimension. So the alpha that you get here is going to be independent of the dimension, but you do have a log factor that depends on the dimension. So it's not completely dimension independent, but it is a lot better than the results that we had earlier. Okay, so that was really all I wanted to show you today. So just to briefly summarize, so we used Gaussian process regression to essentially learn the unknown function f from n function values. We showed that you get a form of posterior consistency. It was the mean of the posterior tends to the true function f, and the variance goes to 0. I showed you the L2 norm estimates because those are the ones that are interesting to us in applications. So for example, if you think of approximating the forward map in a Bayesian inference problem with Gaussian process emulators, that's what you need. But we also get pointwise error estimates and error estimates on the higher order derivatives. And yeah, just the kind of main takeaway message again, that this is actually quite robust. So the fact that you do have to learn these hyperparameters and you don't really know what they are, that doesn't really matter. You do still get convergence. You don't always get convergence at the optimal rate. So that's something that you would have to be aware of. But most of the time you still do get convergence, and the only time that you possibly don't get convergence if the prior is too smooth. So if you're overestimating your smoothness by too much, then you might get some stability issues there. Right. If you're interested in the details, there's this paper here, and I've lost a bit track of time, but if there's time, I'd be happy to take more questions as well. So thank you.